All right, let's say if I have a kilogram of water and a kilogram of iron. Okay, now let's say if I heat them up, add 1,000 calories of heat into water and iron, same heat there. Question to you, do you think that the temperature of water and the temperature of iron will go, of course, they both goes up, but will they go up to the same temperature? Probably not, right? I mean, use your common sense right here. So heat up this, add the same heat to water, add the same heat to iron, same weight, but the temperature of water doesn't change as much as iron. And you guys know iron, metals usually conduct electricity and heat well. Okay, so what happened is, so add the same heat, but the temperature of water doesn't change as much compared to iron. Okay, and that's because the specific heat capacity. All right, let me define the specific heat capacity real quick. So the specific heat capacity is the energy required to raise the temperature of 1 gram of substance by 1 degree. Here's the meaning of it. So if I have the same amount of water, like same weight, water, aluminum, iron, and carbon, they all have the same weight. These are specific heat for each substance. Okay, water have a specific heat of about 4 joule per gram per Celsius, which means that if you want to raise a temperature of water by 1 degree, that's the heat that you need to add into water. All right, this is per 1 gram water. If you compare to the specific heat of water to the rest, 5 to 10 times higher than the rest of the periodic table, actually, right? Which means that you need more heat to raise 1 degree Celsius of water compared to the rest, right? 5 to 10 times much higher, all right? And the specific heat, that's an equation for specific heat, equal to the amount of heat that required to raise a temperature of 1 gram of substance by 1 degree Celsius. Okay, so if I can rearrange this equation, I'm going to get Q equal to ms delta T. All right, that's a heat capacity equation. So we're going to use this to do this equation, this problem together. All right, how many kilojoules of heat are required to raise the temperature of 120 grams of water by 5 degrees Celsius? Okay, so let's say I have 120 grams of water, and then I heat it. So I don't know how many kilojoules, but the change of temperature is 5 degrees. Before and after is 5 degree difference. So, right now, what is the heat that we add into this water? 120 grams of water. So Q equal to ms delta T. The mass of water is 120 grams. The specific heat capacity, so you have to look back to the previous slide. So 4.184 joules per gram per degree Celsius. Okay, can be Kelvin, can be Fahrenheit, it's gonna be Celsius, and times 5 degree different. Do the math there. 2510.4 joules. All right, make it a scientific notation. So 1, 2, 3. So 10 to the third. 10 to the third is kilo. That's a kilo. Okay. 2 sig fig. Is it 2 sig figs here? Write it down. 2.5 kilojoule. That's the answer. All right. So we're going to need 2.5 kilojoules to raise the temperature of 120 grams of water by 5 degrees. All right, next one. A chemist tests the property of 230 grams of sample. So it's unknown metal. He finds that this amount of energy increased the temperature of metal from 25 degrees to 30.88 degrees Celsius. What is the specific heat of this metal? Okay, so we have 230.0 grams of metal, the unknown metal. The starting temperature is 25 degrees, the initial temperature. And then we heat up this metal, right? So add 17 joules to this metal, and the temperature goes up to 30.88 degrees Celsius. Okay, so I know that I'm going to need the delta T, so I'm going to calculate right here. So subtract 30.88 minus 25. So you get plus 5.88 degrees Celsius. Okay. All right. So what is the specific heat capacity of this metal? So, well, Q equal to ms delta T. You got only one equation. Rearrange this equation. So S equal to Q over M and delta T. Look like that. If you not following, so basically I just divide both sides with M delta T. So M cancel out, delta T cancel out. Okay. The rest just plug in, guys. So Q is 1217 joules. Mass is 230.0 grams. And delta T is 5.88 degrees Celsius. Do the math there. Ta-da. Okay, 3 sig figs here, 5.88, not 4. So watch out then. So you get 5.88 as a 3 sig fig right here. So we do 3 sig figs. Write them up. 0.900 joule per gram per Celsius. What aluminum is this? What aluminum? Did I say aluminum? Jesus Christ. What metal is it? It's aluminum right here. So the specific heat capacity of a matter is a property. So each matter, each substance, they have their own specific heat capacity. So it's like density, right? You can use the value of specific heat capacity to identify matters. It could be gas, liquid, or solid. In this case, it's aluminum. There we go. All right, a little bit application about the specific heat capacity here. So something that you should know. Water has a very high specific heat capacity, right? So high heat capacity means an ability to absorb heat or release heat without significantly changing phase or temperature. Imagine this: if the water has low specific heat capacity. When, let's say, the day change, like the temperature in a day changes a little, water either vaporized or got frozen right away, right? Can you imagine? So our human body contains 72% of water, and in a hot day, the water just vaporized out of your body. Or in a cold day, it's just cold, not at a freezing point. In cold day, water just frozen up. Right, so that's gonna be weird, and that's really detrimental to your body, because our body contains our enzyme, DNA, biomolecules, cells, all those reaction or biological chemical reaction in our body function best in water at anywhere from 20 to 40 degrees Celsius. Beyond those, our enzyme, our DNA can't work. Right, so having a lot of water in our body is a good thing for all the enzyme, DNA, and cells, because they can function, right? When the temperature is hot or the temperature is cold, the water in our bodies stay pretty much the same temperature. Actually, it stays at the same temperature, 37 degrees Celsius. And that allows our enzyme, DNA, cell to function properly so we can live, right? So that's the reason we have our body contains 72% of water, and water is one of the substance that has high specific heat capacity. Okay, not like if you compare the specific heat capacity of water to others, gas like 1, ethanol 2.597, oil, gasoline, none of these have high specific heat capacity, right? Than water. Okay. So rock had low specific heat capacity. It's probably somewhere in Arizona. You can fry eggs on the ground. So, all right, and of the enzyme, DNA, yep, yeah. Optimal temperature of all these guys work well at about 30 to 40 degrees Celsius, or 86 to 104 Fahrenheit. Okay.